So let us now go to applications. Since there exists no concrete mouse for general games, and we even saw in this simple example of prisoner's dilemma that you cannot bound that in general, because in prisoner's dilemma, for example, simple as it is, a two-player game with two strategies for each player, you can vary the parameters, and then you have this price of anarchy and price of stability. They are the same because there is only one equilibrium indefinitely, as large as you want. That's what you can have there. So we need to study concrete cases, and luckily many models of interest, in particular network models we are going to do now, are amenable to bounding. So let us consider several classical examples in several important classical areas. So first, non-atomic network routing. Non-atomic means that you treat the routed commodities or the routing flow, abstractly speaking, for whatever its models, as something which can be indefinitely divided. So that's why it's non-atomic. There is no one like who has to only move things by a given chunk. That's something you can split as you want, well, given some conditions. If you want to be in an equilibrium, for example, that they are going to talk about now. Now, since the model actually talks, what we model here is infinitely many players, each one controlling an infinitesimally small portion of the flow. That's not something which fits our model, so we need to give a new formalism here. You will see that it actually fits the definition, as I said, that you have infinitely many or indefinitely many, but I think it's better when it's infinitely many. You can think of those players who each contains one infinitesimal part, and that's the intuition which we are going now to see how we can model that. And that what we do now in this application. So there are source and sink paths, K paths, S1, T1, source one and sink, source one and sink T1, and source K and sink T2. K there are K paths. These are not a path. These are paths we model in infinitely many paths. This is just paths of source and sink. So paths from which to which you have to root something, and you need to root for each such pair a commodity of size Ri. So for pair I, you need to root commodity of size Ri through path given in the set of paths, which is denoted by the letter calligraphic Pi. Now a flow vector, which is basically the parallel of a strategy profile here, and of course the costs are going to parallel the utilities. But let's first talk about the flow vector. It's a vector of non-negative numbers of the dimension which is the size of all the possible paths. So you need to give what exactly is the flow through each path, and that's visible if when you sum all the paths in Pi, in calligraphic Pi, or if you sum the flows of all such paths, you get exactly the the commodity, the size you need to root. So you need to root Ri units of something. That's what exactly you get if you sum over all the paths in calligraphic Pi. This is called a feasible flow, and only those are relevant to us. We are only talking about them. So those are parallel to strategy problems. And each edge, now let's define cost functions in order to define the costs. Instead of utilities, we are going to have actually costs here. The players want to maximize. And each edge has a non-decreasing cost, so the larger the flow through each edge, the smaller, or at least not larger, the cost. And that's a function from the positive non-negative reals to negative reals. And the cost of flow is defined. The cost of of a path given a flow vector is defined as the sum of the cost of the edges along this flow. So you go along this flow, and for each edge you look what's the cost of this edge. Given that the flow that flows through this edge. And you sum up those costs. So that's the cost of along a path. Now, the equilibrium here, I've not, by the way, defined yet what is the total cost of a player, because the player can have multiple paths. But let me just define what it means to have an equilibrium, because we don't need the total cost. What we do need is which path to take. So the intuition here is again that nobody can improve. No infinitesimally small amount of flow can improve its fate, given what the others do. So define an equilibrium flow as a feasible flow f. Such that for every we are always talking here about feasible flow. Such that for every commodity and for every path, that such that there is something positive there. So every time there is something we can talk about, some players, and again the players are the infinitesimal particles, but indeed that's the intuition, they're infinitesimally small. As long as there is someone to talk about, there should be no other path which is better for any small path. So that means that for every path, any other path, P prime in calligraphic PI, the cost. Now, I don't talk about another flow because again, the changing part can be infinitesimally small. So I'm talking simply about what happens under the given flow F, and the cost of the other option should be at least as what the cost of this option is, or what the cost of this path under the flow is. So there is no path any infinitesimally small or large, whatever, path would like to move. There is no better path. That's the meaning of this equilibrium clause, which is parallel, of course, to Nash equilibria in the normal form games what we have been studying. And so what we've defined is that we've defined the cost of a path as the total cost of all the edges along this path under this flow, and we have defined an equilibrium flow where nobody can improve, no little or infinitesimally small path flow has a motivation to move to another path. And now we finally define the total utility of the flow, which is actually the parallel. We don't even define the total utility of a player. We can talk about what is the utility of a path, and actually, yeah, we shouldn't define the utility of a player because the players are infinitesimally small. But the player has experienced some cost along all those paths, and we've defined the cost of the path along the path, and that allowed us to define an equilibrium flow. What we should define is the total utility of a flow. The total utility of a flow, which is parallel to the social cost, is the social cost, you might say. And that's the utility of all the paths we have in calligraphic P. So for each path, you look at what is the capacity, what is the cost of the path, and you multiply it by how many actually take the path, how many people take this, incur this cost, my FP. And the price of anarchy here is defined as the cost of the equilibrium flow. So how much actually the equilibrium flow incurs, as to how much it's worth relatively to the optimum, smallest possible. Okay, so that's what we have. And let us now look at a concrete, simple example. First, a very simple example, then a bit harder, but still simple. So, an application, the same application example. So assume that we have only one commodity, and the commodity is of the unit size. And in this case, of course, we have only one equilibrium when every every xj has to be 1 over m, because that's the graph. Assume you have n parallel edges, which commodity function, which the capacity cost function c of x equal x for every such path, or path has just parallel edges, so there is one edge in each path. And of course, the equilibrium is when they equally divide those source among all those edges, because otherwise there is one edge where I have strictly less than another edge. That's the motivation to deviate. That's again what we defined as an equilibrium flow. So there is only exactly one equilibrium here. And as I said, this has to be 1 divided by the number of parallel edges. So 1 divided by n. And that's a typo. 1, that's y divided by n. Let me fix that. Okay. Now, what is the optimum? Okay, think if you want before and solve yourself. It's not hard. So the optimum, probably intuitively you see that that's also the only optimum. What matters is that that's an optimum, but we can just formally prove it. So let any x1, x2 t left n be the vector of those flows. That's always to be 1. So we can just look about on the first n minus 1 as free, while else 0 and 1. The sum is at most 1, and 1 minus the sum, that's the end part. And therefore the function is, okay, so there are x1 many along the first path, and the capacity is x1, the cos x means x1. x2 many along the second path, and the cos x2, and so on, till 1 minus sum of the first n minus 1 along the nth path, and their cos x the same. And then let's find the maximum of it. So that's simple calculus of multivariate calculus. So inside this domain, we have to actually have, if there is an extremum, if there is a maximum, then it's an extremum. So all the partial derivatives have to be 0. So the partial derivative, you can just check this is the expression. Not hard as you can get, just a little bit of calculations. And that's equal to 0 if and only if all the xj's are 1 over n. And since the second differential is twice the identity matrix, here I mean by capital I the identity matrix, and all its principal minors are 1, so the principal minors, I remind you that those are the determinant functions, the determinant values, of all the submatrices. When you look at the first two, at the square, the matrix entrance in the leftmost upper corner, and then you look at the 4 such entrances. So you look at submatrices from the left upper corner, and all those matrices, because they are submatrices of the identity matrix, they also are small identity matrix. Their determinants, of course, are 1. So all those are called principal minors, and since they are 1 by the Sylvester condition, that means that's a local minimum, and of course that's a set multivariate calculus. So I don't go here into all the details, but that's just a local minimum. And since it's only one, that's also a global minimum, and you can also check that there is nothing which we can maybe missing on the circumference. So that's the only global minimum, exactly as the equilibrium. So the price of anarchy and the stability are equal to 1 here, and I forgot to write 1. And now I've not even defined price of stability here, but simply the worst, the cost of the worst equilibrium flow over the optimum cost. The best. So the price of anarchy is the cost of the largest equilibrium flow over the optimum cost, and the price of stability is the cost of the smallest equilibrium flow over the optimum. Now, please remember, it can be proven that these costs are always the same. So all the equilibrium flows in such games have the same cost. They are not proven that, but it can be proven, and therefore it's customary not to talk about price of anarchy and price of stability. But it can be defined, and in this example, we actually show that the only equilibrium is always optimum. So the price of anarchy, and if we define the price of stability also, they're both 1. Now let us go to another example, which is also simple, and that's actually a classical example. It's called Pigot's example, and that it's interesting because despite its simplicity, it gives actually a bound. It depends the worst price of anarchy which can be. So this optimum, but of course there can be some worst case, and that, as it can be proven, so we will not do this in this course. That's the worst possible case. Actually, that was proven by Ralph Gardner and I think by Tardosh. Both are very famous algorithmic game theorists. I don't know whether it's the first time you hear their names, but those are very important people. And source you have one source S, one destination T. Costs defined by here the function is always 1 regardless the x. Here the function is the value of x. And there is a 1 unit of non-atomic traffic. It's non-atomic network route and everything. There is 1 unit to route from S to T, and since the low edge is always the dominant strategy, the weakly dominant strategy, and if there is strictly less there, it's strictly dominant to move to the upper edge. Excuse me, it's strictly dominant. If there is strictly less there, it's strictly dominant to move there from the upper edge. Then it means that there is only one equilibrium and all the flow goes through the lower edge. Now, we have not defined what it means to be dominant, and of course we can define it, but you understand the idea, intuition, and formally I can say that simply all the flows where not everyone goes through the lower edge are not equilibrium flows, because then it's strictly better to move. The cost of the lower edge will be strictly smaller than 1. And therefore, this is the unique equilibrium, and the unique equilibrium costs are, so everyone goes through the lower edge, so the cost is 1, and there are 1 unit of players who do that. So it's 1 times U1, it's 1. Okay. So that's the cost of the unique equilibrium flow. Now, what is the optimum average flow? Here it's not the same as the equilibrium. Here let's solve it. Now, let's denote the number of those going through the lower edge by x and those going through the upper edge by, then it will be 1 minus x, and because the total flow is 1, so then the total cost is x going through the lower edge. It costs them x each, so x times x plus 1 minus x goes to the upper edge. It costs each 1 because the upper cost is always 1. and that's the function, and that's, again, it's simply in school calculus. It's a parabole goes up like a smiley parabole, which goes upward, and if global minimum is obtained when this derivative gets to 0, exactly when x is half. You can also show its local minimum because the second derivative is positive, but again, it's something we know because it's a parabola also. So that's also the global, that's also the global minimum. So the minimum is attained when x is equal to half, unlike the only equilibrium flow, which requires x being 1. And so we need to split the flow equally for the optimum. And therefore the total cost, the total optimum cost, we substitute a half, and we get 3/4. And therefore the price of anarchy and the price of stability, again, here we again see on an example the same, this example too, and as I said, it can be proven it's always the same. The price of anarchy and stability is equal to the maximum cost, which is attained when you have an equilibrium. So when everyone goes through the low edge, and that we saw that exactly 1, divided by the optimum cost, which we saw it's 3/4. And therefore the price is 4/3. Now, as we defined in the beginning, in a general self-distributing game, the network can be arbitrarily large, there can be arbitrarily many sources and destinations, and the function can look however we want. The network can look however we want. The cost functions can also be arbitrary, just we require that they are non-negative, continuous, and non-decreasing. And for a general game, it can be proven that the price of anarchy is always equal to price of stability, as I said. And in all, if all the cost functions are affine, so it's a linear function plus a constant, then the price of anarchy and price of stability are, as I said, equal, and they're always at most 4/3. And so we don't prove that bound, but if we did, we would see that, we would conclude that our example of, not our, Pigo's example, is simple as it is. It's a worst case example for a fine cost function. So there can be as complicated graph as you want. There's many sources and destinations, but as long as the cost functions are all defined, that's going to always be at most 4/3. The price of anarchy is at most 4/3. And if we do not limit the cost functions, and even in this simple example, even the price of stability can be arbitrarily large. Now, let's go to the next application, and that's network design. And formation game. So that's, as the previous game was about routing, which is a very common thing people study. People often about those network max flow mean cut algorithms and all that. Network design is also a very common thing in combinatorics. And now that's a concrete, we are going to see actually several concrete examples. Now I have to define a general game, which we're talking about here, but that's also a huge domain, which is important. So network design is an important thing. Of course, it models a lot, as you can guess. It's all very practically important, theoretically and practically important thing. Models. So that game is called Shapley Network Design game, and Shapley, it was a very famous game theorist who got the Nobel Prize also. It was very famous in many areas. He left his signature, so to speak. And the Shapley network design game consists of a directed graph, a network, so to speak. Each edge, or each arc, I should say, in a directed graph, but whatever, is endowed with a fixed cost. Now, players, here we don't let anything flow, at least don't think of it. We just think about constructing a network. So an edge costs something. Players, here it's a normal form game. Here it's a game So we define players, strategies, utilities, or costs. Sorry, as in a normal game. It's not like that we have those infinitely many players. Here we are back to our normal framework. So players n from 1 to k instead of 1 to n. Okay, doesn't matter. With sources and destinations as inti for each player, and player I, the strategies are all those paths in this graph which connect Si with Ti. And those are the strategies. So assume there are such strategies, because if there are no strategies, that's not. Then it's that game is it's actually not well defined. Strategies need to be known. So we assume the graph connects each source, each destination. So there is at least one path for each source, from a source to destination for each such couple. Not from each source to each destination, but there is exactly one path from a source to destination for each such couple. Now, the strategy sets all those paths from Si to Ti, and the cost of player I is the total cost along the path that player chooses, but each edge costs not its only its original cost, but it generally costs the cost divided by the number of those who use it. So Fe is the number of players whose strategy or whose paths include this edge, the load on the edge. So the costs are divided equally between the players. And then let's look at a simple example. So first example, it's very simple to be almost funny. So assume you have k players. They all share the same source and the same destination. So source S, destination T. And let epsilon be small enough. Now then, social optimum profile means that everyone needs to choose the lower edge. Clearly, that's that's better for the social society. And this adds to an equilibrium. So there is an equilibrium which is optimum. Price of stability is 1. However, there is also another equilibrium. Now let's first talk about why this is an equilibrium. So this is an equilibrium because everyone who will deviate from the this profile would suddenly pay k instead of paying 1 plus epsilon divided by k. Now, however, there is another profile when everyone plays the upper strategy, and then everyone plays k divided by k, 1. And deviating to the lower edge would make that only deviator, that's the only deviations we look at, unilateral deviations, would make the deviator pay 1 plus epsilon, so it will not be profitable. So that an equilibrium. And the price of anarchy of such an the utility of such an equilibrium is, of course, the cost is much worse. It's almost k times worse. And that's, of course, the worst, socially worse profile. So the price of anarchy is the worst of the best, the worst socially worst equilibrium, which costs k, or the best profile, which happens also to be in equilibrium, but doesn't matter. The best profile costs 1 plus epsilon. And that, so that as close to k as we want. So the price of stability is 1, the price of anarchy can be big here. But is the price of stability always 1 in such games? And now we can stop and think. The answer is no. Maybe I should have put it after a pause to let you think. But anyway, the answer is no. And there is this nice example which shows you that it can be that even the best equilibrium is always worse than optimum. And look, so that's a game. You have k players, you have those sources S1, S2, k minus 1, and Sk. Those are the sources. Now you have a single common target to all of them. So all the ti I equal to t. And the cost adjoint with 1, 1 over half, 1 over k minus 1. I mean 1 over half, 1 over 3, and so on till 1 over k minus 1 and 1k, 1 over k. This edge costs 1 plus epsilon, and those edges cost 0. Now, pay attention to this. Social optimum, of course, is that everyone uses this okay. The path, every player I uses the path first going to B, it does not cost anything, and then going to T. It costs 1 plus epsilon. It's the most expensive edge here, but they all use the same thing, and therefore they all pay together 1 plus epsilon. So the social cost 1 plus epsilon. Epsilon can be arbitrarily small, so it's always better than any other. Now, this is not an equilibrium, however. Now, there's why. Regardless whatever the profile is, for the player K, it's always strictly better to go to T directly. It's always better, even then, because the other option is to go to B and then to go from B to T. But when it goes from B to T, she has to pay at least 1 plus epsilon over K. That's always better than 1 over K. So even if everyone else chooses that edge too, you have to pay more than just going directly. So it's always strictly dominant. So that always has to go there. Now, so delete the other option, and then we have a subgame obtaining. You obtain a subgame, and then you can similarly say that for player K minus 1, going direct to T is optimum now, because, well, at most K minus 1 players use this edge. So if the player K minus 1 goes to D and then to T, it has to pay at least 1 over epsilon over K minus 1, which is strictly larger than 1 over K minus 1, and so on. So you just delete those strictly dominated strategies, and you can also say that you can basically get at a profile which is strictly dominant, and that's the only Nash equilibrium, and that's a profile when everyone just goes along his or her only edge from Si to K to T, and this cost, of course, 1 plus 1 over 2 plus 1 over 1 is 1 over K, which is approximately lambda. So that's called the harmonic number of K, and that's the price of stability is this number, which is the worst what you can get in equilibrium. It's actually the only thing you can get in equilibrium. That's price of stability and anarchy, and divided over the best we can get in equilibrium. Excuse me, with the best we can get in any profile, which is when they all go to through B, and then you have 1 plus epsilon, so which is this harmonic number. That's why it's called harmonic price of stability, as an example, and that's close to lambda, small variance factor. Yeah, small variance factor. Okay. Now, we can ask, of course, does every Shapley value possess a pure Nash equilibrium? Because, yeah, till now, we always had a pure Nash equilibrium here. It was the only one. Here we had several, at least 2. Does every such game possess a pure Nash equilibrium? We needed to make sense from price of stability, because price of anarchy being constantly bound, and the worst thing can actually talk about randomness. But price of stability, which assumes that we concretely give some profile, needs to assume that we play something. So that's why it's important to talk about, if you want to talk about price of stability, we need to know that there is something pure. And the second question is, so what is the largest possible price of stability in a Shapley network design game? And the answers, which we don't prove here, are that all this exists in pure anarchic equilibrium, and the largest price of stability for a sharply network design game with k+, is the one which we saw, the harmonic thing, which again we don't prove. So that example is also in the sense that like Pigo for its kind of game, this example is the worst case for this kind of game, for sharply network design game, from the point of view of the price of stability. And now we are ready for, now we have done, let's now go to the next application, which will be the scheduling games.